Hi, welcome to this lecture on introductory mathematical methods. In this lecture, we will discuss Fourier series. So, the title is Fourier series, can I write an equation for any function? That is what we will continue discussing. What we said is that if you have a periodic function, something that is repeating in space or in time essentially, whatever be the function x or t, if it is periodic, you could write an equation for it in terms of sines and cosines. What we will do is if we have a periodic function f of x, I could write f of x is equal to a0 by 2 cos 0x. Since cos 0 is 1, this will be just a0 by 2 plus a1 cos 1x plus a2 cos 2x plus dot 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 infinite series plus a0 sin 0x. Since sin 0 is b0, I would write a different coefficient b0. b0 sin 0x. Since 0 is sin 0 is 0, b0 this term is irrelevant, plus b1 sin 1x plus b2 sin 2x plus dot 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 infinite series. So, if I specify this coefficient, for example, ai's a1, a2, etc., and bi's b1, b2, etc., I get this function f of x. So, if I specify all these coefficients, I can write down this function. As opposed to this, if I know f of x, I can also calculate these coefficients, and there is a procedure which we discussed. I multiply, if I want to calculate a1, I multiply this f of x with cos 1x and integrate. If I want to calculate b2, I take f of x, multiply with sin 2x and integrate. So, if I do like this, I would get any ai's, an's I want or ai's I want. So, if I in general, if I want to get a whatever be the n, to do that I can have to integrate. I have to take f of x, integrate. A's are coefficients of cos, so I would take cos nx and integrate. Typically the way it is written, minus pi to pi, and I would define this 1 by pi. This is 1 by pi is just a matter of definition. There are different ways of defining it. You can look at in the book. Similarly, bn would be integral, take our f of x. Since bn's are coefficients of sine, I would multiply sin nx and integrate minus pi to pi. It's a matter of definition again, and I would get like this. So, this is the way one would get these coefficients if I know f of x. Let us quickly look at an example. Imagine that now you have a protein or you have a periodic function which has the following shape, which is like this, which is like an inverted L if I wish. So, basically you have atoms which is like this and like this. Okay, so there is also like this. So, beyond up to some value, this is let us call this 0. So, this is my, I would call this as the origin of my graph 0. So, I would call this, if I have a graph, I would call this 0. So, I have 0 here, and it is 0 from some point to some point. So, let us say this is minus pi to 0, the function value is 0, and 0 to pi, this has some value, let us call it h, some height h. And then this will repeat again many times. So, I would again repeat from here to here, it would repeat again. So, this is where pi, it would repeat again. So, I have values here, and then it will go like this. Then again it would repeat So this is my function, which would look like this. If I look at it, it looks like a square wave if you wish. If I specify this height and this and all, then it looks like a rectangular or square wave depending on how you plot it. This looks like a wave front. It's like repeating, any repeating thing would look like a wave. So, but this is basically, as we saw, it is repetition of a function like this. So I have a function, or I have a protein which has a shape like this, and I crystallize it. I make repeats of this in 1D along this x-axis many times. Then it would look like this. Now, what is the equation for this is the question. And to understand the equation for this, we could use the Fourier series. What is the, so this is my example, another example of Fourier series. My function is 0 from minus pi to 0. So this is what the first part is. Minus pi to 0, the function is 0. So here it is 0. 0 to pi, the function has a value h. So 0 to pi, the function has a value h. There is some y value. And again, it repeats. 0 to, in this region, minus pi to some region of a distance of pi, it has a value 0. Then it has a constant value 0, constant value. So this is the repetition of this. That would look like a square or rectangular wave depending on the value of h. Now, we can get the coefficients a n and b n by the definition of integral that we wrote. So you could get a0 by this integral f of x dx. Our f of x is a constant which is h. Okay, minus pi to pi I can do, and which basically I can write as minus pi to pi and 0 to pi. So the first part is 0, minus pi to 0, the function is 0. 0 to phi, the function is just h. So here f of x I would put h. So this is integral h dx, which 1 over pi, it will be just h here itself. So you have this value of h. So I would get a0 equal to h. What is an, which is a1, a2, etc. I have to multiply h, which is my function, cos nx, and integrate for various values of n. So whatever value I take, n is equal to 1, h is a constant. So integral of cos would turn out to be 0. So this function would turn out to be 0. I urge you to integrate this and check this yourself. You can check 0 to pi cos 1x, which is cos x, would be 0. There will be a plus part and a minus part. They will cancel. Area under this curve, signed area, would be 0. Right? Similarly, so what are we saying? We are saying that integral 0 to pi cos x, this you calculate and you would get an answer which would be 0. If I have to plot, the function would looks like this. So there is a positive part and a negative part. Right? So there is a positive and negative part. They will cancel each other and you would get the answer to be 0. So that is what the reason one would get 0 for any value of n. What is the b values? Bn. Bn, again this integral h sin nx dx. If I do this integral, of course integral of sine is cos, and if I apply the limit 0 to pi, so integral of sine is cos, if I apply the limit 0 to pi, I would get 1 minus cos n pi. So please do this carefully. So for when n is odd, that is n is 1, 3, 5, etc., this would be 2h by n pi. When n is even, this would become 1 minus 1, 0. So you would get answer to be 0. So when n is even, bn, that is b2, b4, b6, etc., 0, b1, b3, b5, b7, etc. are 2h by n pi. What does it mean? Bn is 2h by n pi. What does that mean? So Bn is 2h by n pi for all the odd values, that is n is equal to 1, 3, 5, 7, etc. And Bn is equal to 0 if n is 2, 4, 6, all these even values. So this means B1 is 2h by 1 pi, B2 is 0, B3 is 2h by 3 pi, and so on and so forth. So you can get all the B values and A values, and if you know all the A values and B values, we can write the series f of x as h by 2, which is the first term. Next term is 2h by pi sine x. The next term is, even terms are 0. So the next term is 2h by pi times sine 3x divided by 3. The other next term is 2h by pi sine 5x divided by 5 plus dot dot dot. This is an infinite series. So we have an equation for the protein, for such a repetition of this kind of a protein that we saw. So what did we start with? We started with a protein which is like this. We started with a protein like this, and this was repeating. If I have such a repeating protein which I want to write like this, so if I have a protein which, or any molecule which has this shape, so these are, and if I repeat this many times, again I repeat, again I repeat. So if I make a periodic array of this protein, I can write an equation for this, and that equation is what is written here, which is, let me write quickly here, the equation is f of x is h by 2, where h is the height, this height is h, this height is h. So h by 2 plus 2h by pi times sin x plus 2h by 3 pi sin 3x plus 2h by 5 pi sin 5x plus dot dot dot. So I have a infinite series like this, which would be an equation for such a repeating protein. So I can write down an equation for such a repeating protein, which is nothing but a series like this. Why did I use? I just used a simple idea that any periodic function can be written as a combination of sines and cosines. Now let us plot this and see. Let us plot this and see. So if I plot just these two terms, like if h by 2 is just a constant, if I add one more term, first sine term, you will get 2h by pi sine x. So this is like a sine x, and if I plot, it would look like this. If I plot two terms, which is 2h by pi sine x plus 2h by 3 pi sine 3x, if I add these two terms with h by 2, I would get a shape like this. If I add one more term, it would look like this. If I add one more term, it would further look like this. So now it is coming closer to a wave, which is like a rectangular or square shape. So I have now up to sine 7x by 7. If I add one more term up to sine 9x by 9, I would get something I can approximate to the shape that we have here. So I can approximate to this shape that I have here, except some wiggliness here, except there is some wiggliness here and some wiggliness here and so on and so forth. Apart from this wiggliness, I can equate this pretty much like this. So I could essentially write an equation here, which is like a repetition of a protein, which is this part, right? If I just take this part, this equation is essentially given by this. So this is the idea. We can, if I have a repeating function, if you have a crystal, you could imagine that is like a repeating function, and you can write an equation for this. Now, it turns out that whenever you do a scattering experiment, you will have sent some kind of light wave. X-ray waves are also some kind of light. It's not visible light, but some electromagnetic waves. They scatter on a periodic function, a crystal or lattice, and when you collect the light coming out of after scattering, all the optical processes will happen and you collect the light. It turns out that from that light, one could back calculate the shape of this protein by doing some mathematical operation which is related to understanding of this Fourier series. So once we know the Fourier series, we can understand how that back calculation is. That is the interesting thing, how this is going to become useful. Just to think of it, let us just suffice to understand in a simple terms. I have this f of x, I have this f of x, which is my periodic function. If I specify all this a0, a1, etc. and b1, bn, all this bn values and an values, if I specify this, I can get f of x. As I said, if I can plot an versus n and bn versus n, for each n value, I could plot the values of ans and bn. So what does it mean? N is equal to 1, the a value is this much. So this is 1. N is equal to 2, the a value is this much. When n is equal to 3, the a value is this much. When n is equal to 4, the a value is this much, and so on and so forth. Similarly, here also, when n is equal to 1, the bn value is this. When n is equal to 2, the corresponding bn value is this height. N is equal to 3, the corresponding bn value is this. When n is equal to 4, the corresponding bn value is here. So by drawing a graph of ans and bn's, which looks like some peaks. So if I specify some peaks, that is equivalent of specifying this function. In simple terms, you could imagine that when you do a scattering experiment, you might get just this ans and bn's. So this, if I do an experiment, if I can get ans and bn's, which are some peaks like this here, if I get these peaks ans and bn's, which are peaks which if I can get this ans and bn's from my experiment, I can use that in my equation and back calculate this f of x. This kind of idea, I am simplifying the idea a little bit, but some version of this idea, some advanced mathematical version of this idea is essentially what is being used in many of this scattering experiments, including X-ray and many scattering experiments. What does it mean? When we do experiments, we get equivalence of ans and bn's. You can combine an and bn and write a new function called cn, then you would get just cn. So let us quickly see that. So what do I have? What am I saying? If I know an and bn, if I know the values of all values of an and all values of bn, if I know this from experiment, I can get my f of x. If I do an experiment, I can get this an and bn. I can also define some function cn, which is some combination of an and bn, and experiments might just give this, and it's also enough to get this cn, and that is also enough to get this f of x. How, this is not very important, but I just want to tell you the idea. Let me quickly tell you how to define a cn, which is sometimes useful. It turns out that if I use cos nx plus I sin nx, I is root of minus 1, this I is called imaginary number root of minus 1, I can define cos nx plus I sin nx as e power I nx. Then I can write f of x as just cn e power I nx. So instead of writing this whole cos and sine, I could just write f of x as sum over n Cn e power I n x. This is possible if I define Cn appropriately, but e power I n x is nothing but cos nx plus I sin nx. What is I? I is nothing but root of -1, which is called the imaginary number. So if I can simplify the an and bn in some particular manner. It's just a mathematical trick. It's nothing physical about it. It's just if I use this mathematical trick, I can define this and I can get e power I n x written in this particular fashion. If I do this, I can get Cn appropriately by doing integral of f of x multiply with e power I n x. So that is, if I want to get a coefficient, I can multiply e power I n x with f of x and integrate, and I would appropriately get the values of Cn. So for example, Cn I can get as 1 by 2 pi minus pi to pi f of x e power minus I n x dx. This would give me Cn. Now how do I define Cn? So there are various interesting ways. So a relation among the coefficients can be designed in a slightly complicated way. It is not very important to understand everything of this in detail, but this is just to show you that we can define an, bn, and we can combine them to get Cn. And once we have Cn, I can write f of x as some coefficient of, we can write f of x as an infinite series in this particular manner. And if I have this infinite series, I could get f of x. If I know specific Cn's, I could get the values of f of x. So in other words, what would it also mean? So what are we saying? If I specify this coefficient Cn values, I can get the corresponding f of x. This also means that if I have a protein or a crystal or a periodic function of our interest, I can do an experiment. I can get some Cn values. So if I can plot Cn versus n and get some value. So let us say, so for some value Cn is 0, some other value Cn has some value, some other value Cn has some other value, for some value Cn is 0 again, so some other value Cn has some other value. If I get some peaks like this, Cn as a function of n, some numbers like this, so this is all corresponding y value. So I have a corresponding y value here, I have a corresponding y value here, I have a corresponding y value here. So if I know the corresponding y value for a given n, so this is 0, 1, 2, 3, 4 and so on and so forth, I can reconstruct the f of x. And one can, for simplicity, let us think about in the following way. We are doing a scattering experiment, and from the experimental data we are getting Cn values, and then we can reconstruct f of x. That is the idea, and many experiments can give these coefficients Cn's. And a little bit more about this we will learn in the coming lecture, and we will try to understand this in detail a little bit more, and how to play around with this and do something more in the next lecture. So with this, I want to summarize by saying that any periodic function can be written as some combination of sines and cosines, which in terms can be written as e power I n x, some exponential function e power I n x, which if you wish is like a wave, sine and cosine is like wave. So if I do a scattering experiments with some wave like light, for example, from that experiment I can get the coefficients an's and bn's or cn's, and from that we can back calculate this function f of x. So, that is one way of thinking about it. In the next lecture, we would a little bit more discuss important things related to this. With this, I will stop this lecture and continue later. Bye.